Okay, here a Boltzmann distribution for a sample of reacting gas at a constant temperature is shown. The activation energy for the reaction is marked. Point X shows the number of particles whose energy equals the activation energy. The temperature of the sample of gas is decreased. And then which point could show the number of particles whose energy has the same as activation energy at the new particle? So you're looking for when they're the same as activation. Now, if temperature is decreased, remember it's the number of particles that will have less average kinetic energy. So we're looking at the peak being shifted. Now, that means we're looking at D. Okay, it can't be A because it's asking about activation energy. Okay, although A is possibly at the curve, but it can only be D because the activation energy is not being shifted. That's only with the catalyst. Okay, 2. Crystals of copper 2 nitrate are prepared by adding an excess of malachite to nitric acid. The formula is that, and then 12 grams of malachite is added to 30 centimeters cubed of 1.5 moles per decimeter nitric acid. What mass of malachite is left unreacted when the reaction is complete? So what you first need to recognize is that you need to write this as a balance equation. So our balance equation is plus nitric acid forming copper 2 nitrate, right? Because we're saying that this is an hydroxide plus a hydroxide and a carbonate in the same compound. And if we add an acid, we will form a salt, and in this case our salt is copper nitrate. And then looking at just the hydroxide part, we are having water, but because of the carbonate part, we're looking at carbon dioxide too. So if we had to balance all that together, okay, this is 2 coppers on this side, and that means we have 4 nitrates, 4 here, and then if we count the number of carbon is just 1, and then hydrogens, we have 6 hydrogens, and that's 3. So now that we have a balance equation here, let's do the mole calculation here. Don't forget to divide by 1,000, 0.045 moles. Now we can see here the mole of nitric acid to the mole of malachite is a 4:1. So that means the mole of malachite is 0.0125 moles divided by 4. And if we had to now calculate the M of that, the mass of that times it by the MR, we get 2.48 grams. However, that's the malachite that has been reacted. We're saying what has been left unreacted, so we have to say 12 minus 2.48, and we're looking at 9.51. The answer is D. Okay. X and Y elements from the same group of the periodic table. The 5th to 9th ionization energy for X and Y are shown. The table, which row identifies element X and Y. So this is successive ionization. So it's taking one electron after another, and that means you look for the large gaps, large jumps in activation. So the large jumps that we can see here is between the 7th and the 8th one here, and then for Y we're also looking at the 7th and the 8th one. So that means we're looking at both of them being in group 7. Okay, we're saying that this 8th one is the hardest one to remove. That means there's 7 on the outermost shell. Then we can take out argon, neon, argon, neon. So we're looking at determining between whether it's chlorine or fluorine. So in order to determine that, decide between these two. Okay, X's active ionization energy is much greater than Y's. So that means it's much harder to remove X and it's much easier to remove Y. Now if you think about it, it must be much harder to remove an electron from fluorine because it's closer, the outermost electron is closer to the nucleus compared to chlorine. So that means we're looking at C, fluorine being element X. Okay, an ion with 2 minus charge contains 10 electrons and 14 neutrons. What is its nucleon number? So let's say we're looking at X, 2 minus. We're looking at 10 electrons. That means we have, and it's 2 minus. That means we must have gained 2 electrons. Okay, and we're saying 8 plus 14, that is 22, and that is B. Okay, the structure of hormone histamine is shown. Which row contains the bonds X, Y, and Z in histamines in the correct order from smallest to largest? So let's look at these. So for this one here, this is 4 bonds, no lone pairs. We're looking at tetrahedral, which is 109.5. Here for Z, we're looking at 3 bonds, and there is no lone pairs. Remember, double bonds don't really matter in terms of VSEPR. So we're looking at trigonal planar. And here we have our lone pair of our nitrogen. So this means we're looking at trigonal pyramidal. And this is 107 degrees. So if we had to now put them from smallest to largest, you can see X is the smallest, so it has to be A. When an organic acid is reacted with alcohol, a reversible reaction produces an ester. Okay, you should know this. This is your carboxylic acid. Okay, 0.4 moles of organic acid and 0.3 moles of an alcohol are mixed and allowed to stand at 25 degrees Celsius until an equilibrium is reached. At equilibrium, 0.20 moles of ester is produced. Now, what you would need to do for to calculate Kc here is, remember, do your ice table. So now, if we had to do our ice table here, we have this. Now, something that you guys might miss is about water. So water is not included when it's in an aqueous solution, so when the concentration doesn't significantly change. But in this case, it is part of a equation, so it will matter in terms of your equilibrium. So that means we include it. Okay, right, so if we, let's say, assume 1 decimeters cubed, so we don't need to work with volume, so we're just going to work with your moles. Okay, so now we're saying that we started with 0.4 moles and 0.3 moles. So we can say initial. And we have here at equilibrium 0.20 moles of esters produced. So now we just need to look at the changes. So this is 0.20, 0.20, and 0.20. And now when we do our calculations, we can see that we say we started at 0 here, and this must mean the same thing here. And this is 0.3 minus 0.2, 0.20, like that. Now, Kc, remember, is product over reactant. So we are looking at 0.20 times 0.20 from your ester and your water over your acid and your alcohol. So now we've got this, and we can see here we will get an answer of 2. Okay. With question 7, there isn't actually much to it. They gave you all this information, and you just need to recognize that in reality, this is all that matters, the electrical conductivity, right? Good when solid and when molten. Okay, when solid and when molten, we're looking at metallic. Doesn't conduct when in any state, so it has to be molecular. So if we just look at those two, it has to be A. Okay, right, they give you an excess of zinc reacts with 2 moles per decimeter cubed hydrochloric acid. The gas produced is dried and collected, the gas occupies this much at 101,000 pascals and 293 Kelvin. The gas produced behaves as an ideal gas, so this can give you a hint. We're probably looking at PV equals nRT. So we're looking at zinc plus hydrochloric acid forms ZnCl. Remember, zinc we assume is at an oxidation state of 2+, so right now we have this as a balanced equation. So always write your balanced equation out. Okay, so in this case, let's look at how much gas we have. We have N is equals to PV equals RT. So this is 101,000 times by V, which is 1.354 divided by 1,000, because in ideal gas this needs to be in meters cubed. This is the only exception. And then 8.314 R. We have this as 0.63 moles. Remember, this mole is for hydrogen. This is the only gas that's being produced. Now, we can say that with H2 to HCl, it is a 1:2, so we're looking at the mole of HCl being 0.127 moles. And it's asking you for X centimeters cubed of this, so we just need to work backwards from that, and concentrations of V equals N over C, which is 0.127 over the concentration of 2, and here we have 0.063 decimeters cubed, and therefore it is C. Okay, we have hydrogen peroxide placed in a flask and decomposes as shown. The total volume oxygen gas is evolved is 190 centimeters cubed after 90 seconds, measured under room conditions. The rate of the reaction is calculated using the equation shown. So now they are asking you, they gave you the rate, and they want to know what is the average rate of reaction measured in moles per minute. So this needs to be in moles and this needs to be in minutes. So we've only got given it in centimeters cubed. We should get it into moles. So we are looking at, this is also the moles, the volume of oxygen. So we need to actually work out the moles of oxygen and then convert it into the moles of hydrogen peroxide. Okay, right. So mole of oxygen is equals to 180 divided by 1,000 divided by 24, V over Vm, 0.075 moles. Here we're looking at, it is a 2 is to 1, so the mole of H2O2 is equals to 0.015 moles. Yes. Right, so now we've got our number of moles, and divided by the time in seconds, in minutes, 90 seconds in minutes is 1.5, and we get here 0.010, so D. Methanol is manufactured by reacting carbon dioxide and hydrogen together. What increases the equilibrium yield of methanol? So we're trying to increase the amount of products, and we're trying to say what will force it to go into the forward direction. So with pressure, we're looking at always the number of gas molecules. So we're looking at the stoichiometric number. So this is 4 gas molecules on this side, 1 and 1, so 2 gas molecules. If we increase the pressure according to Le Chatelier's, the system will try to decrease the pressure by going in the direction of less gas molecules. So that means it would want to go that way. So that is correct. Right, let's talk about why the other ones aren't correct. Adding an excess of steam. If we say we add an excess of steam here, what the system will try to do is that it will try to oppose that change by removing some of that water. So in that case, it will force the the system to go in the reverse direction, and that means our methanol will decrease. Adding a catalyst, it increases both the forward and the reverse, so there's no change in the yield. Increasing the temperature, we first need to look at what is the enthalpy change of this reaction. It is exothermic, and that means if we go in the forward direction, we are releasing heat, and that can't be correct if we want to, if it's increasing temperature and we don't want it to produce even more heat. It will want to go in the reverse direction. Okay, right. So for 11, which row is correct? They gave you the reaction. Remember, this proportionation is when you have both oxidation and reduction happening. So let's look at chlorine, because that's the only one oxidation number that can change. Okay, you have the oxygen, which is 3 times minus 2, and your potassium, which is 1. That means we're looking at chlorine to be plus 5. Here, this is minus 1, and this is plus 1. Here, this is 4 times minus 2 and plus 1. So the chlorine has to be plus 7. So we can see here that the chlorine went from plus 5 to minus 5. I'm sorry, minus 1, and then plus 5 to minus 7. So there's definitely both reduction and oxidation happening, and we worked out this to be plus 7, so it has to be B here. Okay, 12. A student mixes 25 centimeters cubed of 0.1 moles per decimeter cubed sodium hydroxide with 25 centimeters cubed of 0.1 moles per decimeter cubed hydrochloric acid, and the student records a temperature rise of 2.5, and we're looking for enthalpy change. So we're looking at Q equals mc delta T. And we are looking at the mass of the water. Okay, now mass of water, we're looking at the total number of volume. Remember, 1 centimeters cubed is equals to 1 grams of water. So we're looking at actually 50 grams of water, and C is 4.18, and delta T, doesn't matter if it's in degrees Celsius, we can just have it as is. So it's 522.5 joules. Now, to work out delta H, we're saying it is Q divided by N. Okay, this is 522.5. What is N? N is the N of your sodium hydroxide. So we're actually looking at just this part here. Okay, so N is equals to CV, so we can just say this is equals to the concentration 0.1 times by 25 divided by 1,000, and we get our answer to be 209,000 joules, and this is a temperature rise, so it had to be negative, and that's the wrong one. We're looking at kilojoules. Okay, 13. Okay, we have carbon monoxide and methanol reacting to form ethanoic acid. The standard enthalpy change of combustion. Remember, for combustion, we have always forming carbon dioxide and water, and we have both our arrows going down because we are forming, and we're going from the carbon monoxide to your ethanoic acid. So let's just put all our values together. Carbon monoxide here is negative 283 plus negative 726. On this side, it is negative 874.1. So your final calculation, if we add those two together, is 1009. Your final calculation should be negative 1009 minus, because you're going in the opposite direction to your arrow, minus 874.1, and here you should get your value to be negative 134.9 B. Okay, 14. Carbon react with nitric acid under certain conditions. The products are copper nitrate, water, and an oxide of nitrogen. 3 moles of copper react with 8 moles of nitric acid. What is the oxidation state? So what you have to do here, same thing, you have to say, let's work out the balance equation. And we have some sort of NX OX. Okay, we don't know. Okay, right. It tells you that 3 moles of copper reacts with exactly 8 moles of nitric acid. So let's just try and balance that. Based on that, we have 3 moles here because, trying to balance the carbon out, so it has to be 3. So let's count the total number of things here now. We have 8 N's. We also have, how many O's? We have 24 O's and 8 H's. Okay, on this side, if we just look at the carbon nitrate, we have 6 N's, and we have 6 times 3, right? This is 18 O's, and we have, what was I saying? We're missing something. Yes, we're missing water. Okay, remember the product here is water, so let's have H2O. Alright, so let's try to balance the water out in this case. So because we have 8 hydrogens on our side, let's make that 4. So the hydrogens obviously balance out now. We have 8 hydrogens, and if we add the 4 oxygens from this, we are looking at 22 O's. So if we just minus those out, you can see that we have what's left, N2O2, right? We have 2 O's that's left and 2 nitrogens that's left. So the oxidation state of the nitrogen that is in the oxide present, remember this is 2 times -2, so it's -4, and we're saying that there's 2 of this, so this has to be 2 plus. Okay, 2 times 2 plus, so that it balances out. Okay, all the reactants and products of an exothermic reaction are gaseous. Which statement about this reaction is correct? Okay, so obviously it's about bond energy of products and bond energy of reactants. So we're looking at delta H is equals to bonds broken minus bonds formed. Broken minus bonds formed. And this is your energy of your reactants. And this is your energy of your products. So if you are saying that it is exothermic, that means that this part here has to be much greater than your bonds broken. So your products have to be more than your bond energy of your reactants, and delta H is negative because it's exothermic. Okay, propene, hydrogen cyanide, and carbon dioxide each contain pi bonds. Which molecule contains 2 pi bonds? So if we had to draw these out, that's propane. I'm not going to draw the hydrogens in. We have hydrogen cyanide. Cyanide, remember, C triple bond N, and we have carbon dioxide, which looks like this. So let's just identify the pi bonds. Remember, single bonds are all sigma bonds, and then once you get to double bonds is 1 sigma, 1 pi. Triple is 1 sigma, 2 pi. Okay, there will always be 1 sigma bond. So in this case, all these other ones are sigma. We have 1 pi bond there. Okay, that's 1 pi bond. Here we have 1, let's highlight it rather. We have 1, 1, 2. Here we have 1, one. Okay, which ones have more than one pi bond? It is carbon dioxide and hydrogen cyanide. Okay, Q, R, and S are consecutive elements in period 3. Element R has the highest ionization energy and the lowest melting point between 3 elements, which are the identities of Q, R, and S. Okay, so if we're saying that we're looking at the highest ionization energy, that means we're looking at not the next shell, right? Because it's all in period 3. So that means the highest ionization energy has to be about the number of orbitals. Okay, so what is the hardest to remove out of period 3? So if we look at sodium, magnesium, and aluminium, magnesium cannot have the highest first ionization energy because we have your Na, which is much harder to remove because it's closer to the nucleus, so that can't be right. Okay, now between magnesium, aluminium, and aluminium has actually a lower ionization energy than magnesium, because remember, aluminium goes into 2p, and it makes it easier because of shielding from the 2s orbitals. Three s orbitals. Okay, with C, so with silicon, phosphorus, and aluminium, one way we can look at this instead of ionization energy is that we can look at the fact that it's about the melting point. Silicon has the highest melting point out of all of them because of the giant molecular. Okay, it's a bit hard to determine their ionization energy because they're within those orbitals now. It is, sorry guys, silicon does have the highest ionization energy, but it doesn't have the lowest melting point out of these 3. Okay, so therefore it has to be D, and we can be sure of that because phosphorus is got a higher ionization energy than silicon and sulfur. A reaction scheme for group 2 metal M is shown. So it reacts with oxygen, and we're looking at M. Let's just use magnesium for the sake of it. Okay, so it's a magnesium oxide, reacts with water, becomes magnesium hydroxide, and reacts with sulfuric acid, and we're looking at magnesium sulfate. Okay, so this is just a study question of solubility. With hydroxide, it increases down the group, sulfates decrease down the group. Okay, that's just a study question. Alright, here. Okay, they give you a bunch of different halogens, and they have 9 experiments in which it contains aqueous solutions of U2, V2, W2, which are separately added to separate aqueous solutions containing those ions, which Rove describes those ions in order of their decreasing strength as reducing agents. Okay, reducing agents means how they cause the other ones to be reduced. That means we're actually looking at how easy they are to oxidize, right? If they oxidize very easily, then that means they are a very strong reducing agent. And then we're looking at how quickly it loses electrons. So let's just ignore these ones because these don't have any sort of meaning. If we look here, you can easily lose that electron here and lose that electron here. So that means that it is the strongest reducing agent, because it loses electrons very easily. Okay, and then we have V, which doesn't reduce either, well, doesn't get oxidized into either solution, so that means it has to be the weakest, so we're looking at B. Okay, with this one, it can either be magnesium chloride or aluminum chloride. K is either silicon oxide or silicon chloride. Now, with this one, you actually need to know qualitative. So this comes from your qualitative analysis. And when you have sodium hydroxide and forms a white precipitate and the precipitate dissolves, it is aluminium. So J has to be aluminium. K, adding water, misty white fumes. Remember, misty white fumes means hydrochloric acid is formed, and that means we have to be looking at silicon chloride. Okay, river water in an agricultural area contains all those ions. The water is treated by adding a calculated quantity of calcium hydroxide. What is precipitated when calcium hydroxide is added, right? So when you decide what is precipitated out is what is not soluble. So chloride's always soluble, NO3 is always soluble, nitrate's always soluble. Now we just need to decide between these compounds over here, right? So if we had, could it be NH4OH? Okay. Could it be these two? No, because why? That's just NH3 aqueous. Okay, so that is not a precipitate, that's just a solution. So, and then we decided that it can't be this one because nitrates are always soluble and chloride's always soluble, so it has to be B. Okay, 4 atmospheric pollutants are listed. Which ones form PAN? You just need to know this. It's these two, so it's 1 and 3. Okay, which graph correctly describes a trend found in group 17? Okay, right. Okay. So even if you don't learn these, remember bond length, remember these get bigger and bigger, and that means the actual attraction between the nucleuses and the electrons get further and further, so the bond length has to increase. Okay, van der Waals, this is correct because we have more electrons. Boiling point, it is correct. No, it's not correct. It's opposite. Boiling point increases. Yes, because we get 2, these become solid. And then the bond energy, they also decrease. Okay, same idea about your weaker bond length, weaker bond between your H and I. Okay, so it had to be B there. Gas M is produced when NH4Cl is heated with CaO, which row is correct. So this one is NH4Cl plus calcium oxide will form. Okay, this is one of the ones that you need to know. It is CaCl2 plus H2O becoming NH3. Okay. This is an acid-base reaction, so we are looking at C. (25) Two nitrates decompose on heating according to the equations shown. 1 mole of each nitrate heated separately, the gas produced in each reaction is bubbled through sodium hydroxide. The volume of any gas that doesn't react with sodium hydroxide is then collected and measured, which shows the greater loss in mass, what produces the greater volume of gas. So this is a basic solution. It will react with only, out of all these gases, NO2. So this will get reacted out. Okay, all the other ones are inert and it will just pass through. So we're looking at the oxygen of this, the N2 of this, and the oxygen of this. Okay, if we're comparing, because the nitrogen dioxide got reacted out. So which ones will have the greater volume of gas? It's pretty obvious because you have 2 and 1, and that's only 1, so it has to be NH3. The greater loss in mass is, you're saying that there is more that is being lost from your lead because you're losing, for your ammonia, you're losing all of this. This is all being lost as mass, right? So that means we are just looking at lead nitrate. Okay, here you can see this is being still left as a mass, but everything else here is already gone. Okay, so 26, organic compound X has imperial formula C2H4O. Compound X is reduced by LiAlH4, but not by NaBH4. What is compound X? So, important thing you need to know here is carboxylic acids are not reduced by NaBH4. That's something important. Okay, right. We need to talk about what can be reduced and what cannot be. First, maybe let's look at this hint. Okay, so ethanoic acid is this, and when we get our empirical, it's actually C2H4O, so that can't be right. Ethanol is CH3CHO. This is C2H3O, so this could be correct. For this one, this is CH3, CH2, CH2, CH2OH, and we get C4H10O, and that's incorrect. Butanoic acid is this, just C4H8O2. So it could be between ethanol and butanoic acid. And we said that carboxylic acids are not reduced by NaBH4. That's all we know. It is D. Okay, right. 27. What is the mechanism of hydrogen cyanide with propanol? This one you should just know, it's nucleophilic addition. Okay, right. What compound cannot maybe synthetized from an alkene with a addition reaction? So something important to take note of here is that they cannot form on the same carbon. Okay, so look here. Okay, let's say we have butane. What needs to first happen is you have your 2 PRs, and because of this negative bond, this becomes slightly positive and this becomes slightly negative. This gets broken and this gets attacked. The BR gets attacked. Okay, so that means we are left with one of them that's being bonded to the BR, and then we have a carbocation. So it can't bond onto the same one because it will only make the other one become a carbocation, and that will be open to the electrophile. So that means it cannot bond onto the same carbon based on mechanism, and it can't bond on a separate compound on a separate carbon as well. As you can see, the carbocation forms on that double bond, right? So it will either be right next to each other. It can only be right next to each other for that sake. Okay, 29, asking for polymerization. Okay, remember, it's about this bond that's breaking in this case. And they're not going to create something new. Okay, so this can't be true because it's still a triple bond. Okay, it's only this bond that is breaking. Okay, right, we can see in this one, same thing here. Okay, it's your CH2. It's still a CH2. Okay, because it breaks and it forms the bond, the double bond that's breaking, that will form the extra bond. The H stays. This is correct. And for this one, you can see it's not breaking that double bond. Okay, it's an alkane double bond that you're breaking. Okay, it's tested. Compound T is tested with 3 reactions. It gives the results as shown. Okay, what's this? Okay, remember 2 and DFH4. We're looking at carbonyl compounds, so ketones or aldehydes. No reactions with either of those. We're looking at a ketone. So this is an aldehyde, and let's determine can the other two work. So this is a alcohol can't work. Okay, between these two, those are both ketones. Which one can work? Now there's a trick here, is with C, we have an alcohol. What's really important about this alcohol is that it is a secondary alcohol. And secondary alcohols give positive tests for oxidation. Because it can be oxidized into a ketone. So that means that this cannot be true because we are only looking at pure ketones. Otherwise, it would have given a reaction with Fellings and acidified K2CrO7. 31. Reagent X is added separately to 2-methylbutane-1-ol and 3-methylbutane-1-ol. The visible results are different. What is reagent X? Okay, when you add it to Na, you're just forming a salt. Okay, you're both forming that salt, and they're not going to form those they're just forming isomers of each other, and they're not going to form something that is different looking. Now, alkaline I2. Okay, remember this is your idle form test. It is for your methyl ketone group. Okay, and you can see when we draw these out, we have a methyl ketone in one of them. Okay, we have your methyl ketone here in your first one, so that's why we will form a different one. We will see it differently because we'll form that yellow precipitate. Those two are just both going to do the same thing. Okay, your PCl5 will give you the same halogen alkane, it's just now different isotopes of each other, isomers of each other. Acidified KMO4 will give you just also an isomer of a ketone or an aldehyde, but we don't see a visible difference between those two. Okay, compound Y is hydrolyzed with warm aqueous silver nitrate to form a precipitate that is soluble in dilute aqueous ammonia. Now that is soluble, we are in aqueous ammonia, we are actually just looking at COBr. And if it's dilute, we're looking at now specifically only Cl minus. So we can cancel every one of these out. And between looking at these two, what can form an elimination to form an alkene? Now, same thing here. This has to do with the fact that we have with the mechanisms, right? We need to have a neighboring H so that when the when this bond breaks, and this forms from like that, OH will get to bond with that H. And we need to have a neighboring H so that we can form that double bond. Now you can see here with D, there is no neighboring H. These are both C's, okay? These are both groups, methyl groups. So we're going to look at C being the correct answer. Okay, 33. Propanediol can be converted into 2-chloropropane using reaction M to reagent N. So this is electrophilic sub. And this is going from OH to Cl, and we're looking at these two conditions. So C, which is a study question. Okay. Skeletal formulas of 4 organic compounds are shown. What happens when you heat it with dilute sulfuric acid? Which ones will produce propanoic acid? Okay, so it won't do anything with your aldehyde. With an ester, it will break. With your nitrile, it can form a carboxylic acid. Okay, that's one of the reactions. So it will indeed form propanoic acid. And here, it will also break. But we need to decide what form propanoic acid. Okay, so let's just count the carbons. Okay, 1, 2, 3, that is propanoic acid. 1, 2, that is not propanoic acid. We're looking at the double bond O for the acid part, right? So this can't be right, and we said that 2, 3 is correct, so it's C. Okay, 1 chloromethylpropane and 2 bromomethylpropane react separately with aqueous silver nitrate. Both proceed for nucleophilic, and they give you the time to form the precipitate and the time for bromine. So here what you need to decide is what is the two mechanisms. So this is 1-chloro-2-methyl. So this is a let's just draw it out. I'll show. It'll make more sense once I draw it out. Propane 2-methyl, CH3, and we have our Cl on the end. So this has to be an SN2. Okay, this is a primary halogen alkane. This is 2-bromo-2-methyl. You can see here it looks like that. So this has to be SN1 because this is a tertiary halogen alkane. So now the time for chloro and bromo. Okay, chloro will form faster than bromo, so that means we're looking at T1 is greater than T2. That's just with your silver nitrate test, remember? So let's just put them all correctly now. So we're looking at just T1 and T2. 1-chloro-2-methylpropane is SN2. That is correct. This is not SN2. Okay, for this question, progesterone, they're asking about the chiral centers. So let's count the number of chiral centers here. Okay, remember chiral centers, don't count the ones that have hydrogens. Okay, just count the ones that are not, that have like different groups, right? So here we have 1 because it has 4 different groups bonded to it. Okay. Here would also be 1. Okay, because we have 1 group here, 1 group here, 1 group here, and we have 1 hydrogen. Okay, same idea for this one at the bottom. Okay, we have one group at the bottom and one group at the top. Now, please actually take note, it's because of these two on the end that are a bit different, then those are no longer the same group. But let's say if they were, these two would actually no longer be chiral centers because they actually are bonded to the same group. Okay, so we have this one, by the same logic as the first one, also being a chiral center. This one would also be a chiral center, and then also this one would also be a chiral center. Okay, all the other ones are bonded to hydrogens. Okay, these ones are bonded to two hydrogens each. Okay, that's why we don't count those ones. So if we had to now just check what's happening, we're looking at 6 carbons. Now the one has to count how many carbons are there, and that you could probably do yourself. Or we'll just count it together. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. So we are looking at D as the correct answer. Okay, they tell you a molecule of hexane can be cracked in a number of different ways. 3 compounds are listed. So we have these compounds which can be formed from a mixture of cracking of hexane. So what you should do is actually figure out, okay, so hexane is C6H14. So what can be left when we have each of them? So when we do this, this is C3H6, right? H6, C2H6 as well. Yes, C2H6. Here we have CH2. Okay, that obviously cannot be true because we can't have CH2. So we can take out 3 as an option already. And you can see the answer is B. Cool. Yep, that's it. The diagram shows the structure of 2 isometric dicarboxylic acids, X and Y. X can be reduced to form the empirical formula. So when you have your acid being reduced, you're forming an alcohol. Okay, same idea here. You're both forming alcohols here. And when you reduced, you should also recognize that we are adding H2. So this double bond also breaks. And we have hydrogenation that is also happening there. Okay, so which statement is correct? So let's actually just look at X. Is it a cis or trans isomer? They are both on the same side of that carbon, so it's actually both a cis isomer. Now, what will happen when they are being reduced? Will they be isomers of each other or will be identical of each other? Now, if you look, we have this that will be breaking apart, and when these break apart, we no longer have cis or trans isomers. Okay, so therefore we can't have cis and trans isomers occur from the inability from rotation of that double bond group. So that means we cannot have isomers once those double bonds break. Okay, what's the total number of sp3 hybridized atomic orbitals used in the bonding of butene? So let's draw out butene. Okay, now let's determine what is sp3. sp3, we're looking at 4 bonds. Okay, when there's 4 bonds, it will form sp3. So 1, 2, 3, that is sp3. 1, 2, 3, 4, that is also sp3. Now with the carbons in the middle, they become sp2 hybridized. Okay, this becomes sp2 hybridized. So therefore, the answer here we are looking at is just D. Okay, 40. Okay, they tell you this mass spectrometer that shows the relative abundance of the two peaks with ME greater than 127. Okay, they give you the relative abundance and 129. So remember what you do is that you use the fact that your n plus 1 is 1.1%. Okay, your carbon 13 is only 1.1% present. So the number of carbons is just 1.1 times 5.5 over 50. The relative abundance of your n plus 1 over your total abundance. And here you get an answer of 10. So the answer is D.